All right, in this video, we're going to revisit an old friend, the conservation of energy, to try to understand how fluid flows through pipes. And to do that, that conservation of energy gets expressed in what's called the Bernoulli equation. So, fluid, as we've just seen in our discussion of continuity, accelerates as it goes into a narrowing pipe, right? If the fluid is moving faster here than it is here, then it must be accelerating. What makes it accelerate, right? There must be some kind of force here. And the force that is doing that is the force of pressure. As our fluid moves from this wide area into the narrow area, pressure is doing work on the fluid, okay? This is both because the area here is larger than it is here, and because the pressure is larger than it is here. So we have a larger pressure in our wide space than we do in our narrow space. That doesn't seem particularly intuitive, but it's really crucial here. As our fluid speeds up, pressure is doing work on it, and it's transferring that pressure energy into velocity energy or kinetic energy. That's what this equation captures. And really what it is it's a conservation of energy equation. Pressure energy, if you remember, we talked about pressure as being kind of springs that are reacting back and forth when we try to compress a gas. Well, it's doing the same thing here. Pressure is compressed fluid. That's stored energy that can be either stored as potential pressure energy or transformed by work into kinetic energy. And notice how much this looks like kinetic energy, right? Half times mv squared, except our m is now our fluid m, right? M over volume. So Bernoulli's principle can be stated as a kind of pressure potential energy plus kinetic energy stays constant as we move through a frictionless pipe. Now that last point is key. Everything we're talking about here assumes that we're not losing a lot of energy in our fluid flow. We'll get to that when we talk about viscous flow. But there's another way that we can think about potential energy here, and that's gravity. What if our pipe is moving up or down? And so we can add a third term here to our equation. And this looks like mass times g times height, right? This is just potential energy with a mass over volume term instead of just a plain mass term. And that's Bernoulli's equation. This energy, all this says is the energy in the flow is staying the same as it moves through a pipe. And that energy might be pressure energy, it might be kinetic energy, or it might be gravitational potential. The units of the equation are in pascals, right? We have pressure here. But what are pascals? Well, don't worry too much about my algebra in the middle here, but I'm just trying to convert those newtons into something. And it turns out newtons are joules over meter. And so pascals are equal to joules over meter cubed. And so the units of this equation are energy per unit volume. Pretty cool, huh? You wouldn't think pressure would be that. So we can think of those three terms in here the same way we just thought of energy equations in our last exam. It's just moving between different kinds of energy, pressure energy, gravitational energy, and kinetic energy. And it's going to stay the same as long as we only have non-conservative forces, which in this case, pressure is the only force we're dealing with. So we can do the same kind of trick that we did with normal conservation of energy, and we can look at different points on a flow and see how energy moves from one kind of energy to another. So here my flow has no kinetic energy, or very little, as this plunger is being pushed up. Um, it doesn't have any potential energy because we'll set y equals 0 to this. But it's a large pressure energy, right? Because I'm adding force with my plunger here. And so I've increased the pressure within my container. So I have a lot of pressure potential. At point 2, I have a lot of kinetic energy. It's moving very quickly. It's got a little bit of gravitational potential, but it doesn't have any pressure energy. Why? Because it's open to the air. And if it's open to the air and it's not moving off to the right, then we know that it's at the same pressure as the air around it. So anytime fluid is open to the air, we can assume that its gauge pressure is equal to 0. And then finally here, we don't have any kinetic energy, but we've got a lot of height, and so we've got a lot of potential energy. And again, it's open to the air, so there's no pressure energy. So we're just converting from one kind of energy to a different kind of energy. So let's look at a couple of examples of applications of Pitot tubes, or I'm sorry, applications of Bernoulli's equation. The first one is a Pitot tube, which is a way of measuring a velocity in a flow. And the way that it works is we have, in this image on the right, we have a flow through a tube or a pipe, and we have a point 1 and a point 2. And what happens is we intentionally stop the flow at point 2 by putting this little tube into the flow. And that means we don't have any kinetic energy here at 2. But Bernoulli tells us that the total energy as we move through this flow has to stay the same. So we have kinetic energy and pressure energy here, and it becomes all pressure energy there. How does that help us figure out what our velocity is? Well, we can use Bernoulli's equation and our equation for pressure depth, right? That I know that by depth, my pressure here is this depth here times g times rho. And we can calculate the velocity of the flow. Okay, so we start here, and this is essentially just Bernoulli's equation. We've taken out the gravitational potential terms because it's a flat flow. And we've also taken out the velocity at 2 term because we've stopped our velocity at 2. So this says energy at 1, which is pressure and kinetic, is equal to the pressure energy at 2. So we use this equation here, and we're going to divide out by rho everywhere, to find that g times this h plus the kinetic energy here is equal to g times this h. We can rearrange this then to find an equation for velocity here. So this gives us our free stream velocity. That is the velocity out here, and gives it a nice little equation with 2 manometer heights. And these little guys on the side of the jet, you've probably seen these when you're walking onto an airplane at the airport. Those are essentially Pitot tubes. They're a little fancier than this one here, but they do the same thing. The second thing I want to talk about with Bernoulli, and that Bernoulli helps us understand, is how does an airplane wing work? How does it lift up a plane? Well, you know, that shape of an airplane wing is this airfoil shape. What that airfoil shape does is it forces the air that's going over the top, that reaches the point here, it forces it together. Basically, it creates a bottleneck here, and that because it can't quickly push up all the air that is above it, essentially it's like having a narrow pipe up here as opposed to a wide pipe down here. That means that your air speeds up as it goes through that bottleneck, right? So here in this nice image from this is called computational fluid dynamics, you can see the higher velocities along here. Those higher velocities go over the top of the wing. And if we have higher velocities here, those higher velocities come from the fact that pressure has done work on the fluid, right? So if we have a certain amount of pressure in the free stream over here as it approaches here, some of that pressure is used up to speed up the flow here. And so we have less pressure energy at the top of the wing than we do at the bottom of the wing. There's Bernoulli's equation. So the pressure potential energy is used up to increase the kinetic energy. The pressure goes down. We have more pressure down here at the bottom than we do at the top. And then we can draw a simple free body diagram, right? We have pressure times area. That's the force on the bottom. Pressure times area going down at the top. But since our P term is so much bigger, it creates a lift on the wing, and your airplane flies into the air. So last time we learned, why a steel boat floats. Now we know how an airplane flies. What a class, huh?